afternoon. This is Professor Tim Leung from the math department. Thanks a lot for joining this workshop, the math workshop for the Summer Institute. The whole purpose of this talk is to try to introduce some math to you. I understand that there is no math course in the Summer Institute, right? So for those who might want to learn a little bit more math in the summer, then too bad. So probably this is a chance that you can see some of the math, but I promise that I will not showing you some very complicated math equation. I will not teach you what sort of techniques for doing those integrations and things like that in the calculus. But instead, I will try to introduce you some of the applications in the real life. Some of those applications relates to my personal research or some examples that I saw previously. I think they are interesting, and I hope you also feel they are interesting. Well, from the registrations, I think there are around 20 some students, but right now we got around 10. Maybe we can still wait for a few minutes before I start the talk. I have around hour and a half for the whole event. I think I will spend around an hour and 15 minutes or so in my presentations. And then if we still have time, then I will try to do a demonstration. I will do a demo, writing some program together with you, showed you some applications. And if we still have time, then I will try to introduce our science program to you. In case if you want to see some related math, and if you want to study at HAST, then what would be the way how you can get admitted? Okay, so I'm not sure your background, but it might be a little bit too early for you to listen to those admission type talk, but I think it won't hurt. I don't think there's attendance for this sort of event. It's more about your personal interest. And if you want to know a little bit more, definitely try to contact myself, or you can, you see an account, there's a HAST admin. If you want to get more information about our admissions, feel free to contact us. We can definitely send you more information a little bit later. Okay, so maybe let me try to share my screen first. Okay, so so this is my talk. So I'm Tim from the math department, but at the same time, I'm also helping the School of Science to do the admission. So I know a little bit about the admission status and process. So in case if you want to ask something related, feel free to send a message to me. And in case if in the talk you got any question, feel free to send me a message. Okay, so we try to make this event more relaxing. Okay, so very informal, nothing very serious. And I can assure you that all the materials I cover in this talk will never appear in your exam. So it's not exam oriented. So enjoy and relax. Okay, so maybe let's start my talk. Now, the whole purpose of this talk is to introduce math to people. I understand that many students, probably not you. Well, you selected to do this talk, so probably you might feel a little bit interested in doing math. But in general, I think a majority of students nowadays they're afraid of math. When they heard of math, it's more in their mind. So that would be something they would imagine on the right hand side. Okay, so that is a very old image I found online. I'm not sure whether that's real or fake, but the important thing is the content on that page is pretty much cover everything in the first year in the university first year math curriculum. So you see it starts from some pre-calculus and then the limit, differentiations, and then all the way up to some very complicated optimization problem, things like that. So those would be the thing the student might first imagine if we ask them to do some math. And that's actually quite scary. I mean, of course, there are challenging problems that student might not be able to solve, but then at the same time, they might feel, oh, there's so many things I have to memorize and it's so difficult. But for those, I hope in the audience, you don't feel it that way. So the purpose of this talk is try to introduce our understanding of math to the general public. Now, the next questions I would like to ask is, so what is computational math? If you have never heard of those terms, then you might imagine, there are lots of calculation, right? So computational, so that means I have to compute certain thing, right? But that's not exactly true. Here's the reason. There are many math problems. I'm sure you are able to solve some of those. For example, on the top right corner, this is a typical integration problem. Okay, so from calculus. If you learned, if you're doing the DSC, the local curriculum, then you should have learned those in M1-2. If you know a little bit calculus, then you see this is a very typical type, probably it's an example problems in the lecture. The very first things you learn in calculus. So this is okay. This is indeed a calculation problem. Okay. Now there are some other problems you might know. For example, this little one, just a quadratic equation. You learn it a little bit earlier, I guess. On the right, bottom right corner, so this is a matrix problem, AX equals to B. If you learned linear algebra, okay, so if you know linear algebra, then you know the notations of matrix vectors, and so you know the matrix inverse and etc. So this is kind of known to students who took the linear algebra. But even if you don't, then you know how to solve a system of linear equation, two equations, two unknowns, and you know substitutions and things like that. Essentially, you are constructing the inverse of certain matrix, and so the solution x equals to a inverse b will be more like pure math notation. We don't really calculate too much here, but then it is more like a notations that we use. But if I specify the size of the matrix, like what you're seeing in this problem, if the size is like 100 by 100, well, I can still do substitution, right? So I just eliminate all those variables one by one, all the way up to 1, and then we solve backward, right? So that's the substitutions. But the issues is that for such a big matrix, one, calculations itself, you can easily make a mistake. Well, honestly, if I need to do a 3 by 3 matrix, so meaning 3 equations, 3 unknowns, I'm sure I will make a mistake somewhere. So that is not a hard problem. It's just one, we can easily make mistakes if we try to do those calculations by hand. The second problem here is that it just takes forever. Okay, so you can imagine how much time you have to spend if you are asked to solve a 100 by 100 system. Okay, so this is a problem that we can do, but we do not want to do. Okay, so there are all sorts of problems. Not only this, but there are many types of problems with similar difficulties. We know how to do it. We can do it by hand. It's just we don't want to do it by hand. No, but then at the same time, there are problems that we are not able to solve it by hand. One example is this one. This is a simple question to ask. All I want to know is just to find the root of a function. The function is just square root x minus cosine x. Not too complicated. It's just a square root function and then a trigonometric function. But it turns out that we are not able to find analytical solutions. We cannot do it by hand. there's no closed form solutions that we can derive. So in a similar difficulty, a problem with similar difficulty would be the one on the bottom left. It just, once again, another integration problem. It's a definite integral. The answer is just a number. But then we are not able to find the antiderivatives of the integrand. Okay, so if you know what it means. Okay, so you're not able to find a function so that its derivatives is exponential minus t squared. So we are not able to find the antiderivatives, and so that means we are not able to evaluate that definite integral by hand. Okay, so from this page, we know there are problems that we do not want to do, even though we know how to do it. There are also problems that we simply do not able to do it by hand. And so that's why we need computational math. Okay, so computational math does not mean just simply do the calculation, but it actually consists of more information than that. We want to teach the computer to solve all those problems for us. Okay, so that the computational actually means using computer. Okay, so we're not doing it by ourselves, but instead, as a human, we need to teach the computer to do all these things for us. And the way to solve those problems, we would call it an algorithm. Okay, so we need to decide certain way to teach a computer, if you see this sort of problem, then you will try to follow this recipe and try to derive certain solutions. And those solutions might not be exact. We know very rarely, unless you're trying to do some symbolic computation, well, computers nowadays, or human at the back, is powerful enough and clever enough to try to solve a problem analytically, and think of a way similar to human. So if you ask them to do some a symbolic computation, meaning that I'm not asking for a number as a solution, but then I need a closed form expression, computer might be able to do some of those problems for you. But in general, let's stick with the numeric computation. Now, for those, we always will get an approximation, meaning that the number or the solutions that you get from the computer are always different from the exact solution. Okay, so that part is called computational math. We try to develop recipe, or we call it an algorithm, to solve certain math problem. Now, a related field in mathematics is called applied mathematics. So applied mathematics will concentrate on applying those algorithms to solve some real life and very complex problem. Okay, so some examples that we are going to see can belongs to the computational math, depending on how much emphasis that you would put to the application. Then some of those can also be applied math. Okay, so those are some very general and broad definitions. So sometimes when we do research, it could be a mixture of all these two things. So it might be very difficult to whether classify certain research belongs to computational math or applied math. Very likely, the journal article or certain type of research might first develop certain computational numerical scheme. That's the algorithms that we just mentioned, and then applied it into certain applications. So in that sense, this sort of research is both computational and applied. Okay, now very different. So the concept here very different from the pure math that you might be more familiar with. So pure math, the questions that they ask will be very different. We saw an example like AX equals to B, where we try to solve a system of linear equation. It's a linear algebra problem. To pure mathematicians, what they will ask is whether the system got a solution, whether the solution is unique, and that would be it. So if I know I have a solution, then the solution would be simply A inverse times B. Okay, so that would be it. So that's pure mathematicians will do. At most, then they will say, well, if you really want to solve certain problem, then there is a Gaussian elimination. Then just apply Gaussian elimination, then you can compute A inverse B, and that satisfied all the pure mathematicians. Now, but then to computational mathematicians or applied math people, the thing that we will ask will be slightly different. We know Gaussian elimination, so eliminate the variable, will not be practical even on computer if you try to solve a system of, I don't know, 10,000 by 10,000. So it would just take too long to get the solution. So we would like to think of a way to approximate the solutions in real time, meaning that when I press the enter in the computer, I would like to see the solutions almost immediately. Okay, so that's real time. I want to derive or develop certain algorithm, a recipe, to ask the computer to do those things for us. If I can get a solutions from that program, then I would also like to know how good those approximations would be. Okay, meaning that would it be possible to estimate the error in the solution? And the third questions, applied math or computational math people will ask is that, will this particular method always work? Would there be certain scenario when I plug in certain type of matrix, the recipe or the algorithm will break down, whether that would be possible? We would try to avoid that and things like that. And so the keywords that we will use would not be existence and uniqueness like the pure mathematicians, but instead, the keywords that we'd like to do is algorithm, meaning the recipe, the approach to solve that mathematical problem, the accuracy, so meaning that how much error is that in the solution, convergence, whether when I do the recipe, it will indeed give me certain solution, stability. If I perturb the problem a little bit, well, it happens in real life. We got all this perturbation because there are always uncertainty in the measurement. So many applications, we are not able to provide all the precise measurement. So the mathematical problem that we are going to solve might not be that precise. So if we are perturbing, if we are changing certain numbers in the problem, we will still be able to get some similar answer. So that's a stability concept. So we are asking for different questions, very different from what pure mathematicians will do. Okay, so this is a general introduction to computational math. So what I'm going to show you today will be 4 applications and 4 examples how we will see all these types of computational math in real life. You might not see those things immediately in your daily life, but then I'm sure you will see some of those applications somewhere in your daily life, but then you never notice. The first applications that I'm going to go over is called the social segregation. It sounds like economics or social science type problem. So I'll talk about what is that a little bit more precisely in just a second. But then it's actually a math problem. People actually convert that into a math problem, and then the problem itself would be a good fit to computer. So then people actually apply the computer and try to study the social segregations and try to see what's the cause of it and try to explain why we have segregations. The math itself, well, even though in my introduction, it's not that complicated, but then people actually convert it into a partial differential equation problem. So it's a very mathematical derivations. I'll try to go over that in just a second. Second applications that I'm going to do is digital image processing. Then you will definitely see it every day. Even right now, when you're looking at your computer screen, there are lots of digital image processing going on. Even when you use a cell phone to take picture, the reason why the picture looks so good probably not because of the lens, but probably because of the image processing tools implemented on the cell phone. So the cell phone nowadays is more like a computer, so it can do lots of things, and there are lots of mathematical tools and model behind to improve the quality of the image. So you use it every day, every minute, even now, but you never notice. So I will tell you some of those applications in just a second. Third applications is a physics-based simulations for filmmaking. So it's a new trend. It's different from CG, computer graphic, years ago. I will show you some example, and then you will see the improvement in the quality of those movies. Okay, so and then when you go to a theater to watch movie, you never know, there are lots of math behind, and it's actually there are a company like Pixar, Disney. Well, they're not only a company for movie making, but then they're actually a math research company. Okay, so that's I hope that's a surprise to you. I will talk a little bit more on that as a third example. If I have time, I will also try to do a demonstration for you. And then the last example, it sounds a bit more academic. It's very traditional. It's very traditional already, even though computer appears I don't know, definitely less than 100 years, but then it becomes traditional. It's a CFD problem, computational fluid dynamics. I will try to link this back to some of the problem that I showed it to you a little bit earlier. Okay, sounds good.